Today, we're diving into the ocean's silent struggle against climate change, specifically how two significant ocean belts are warming at an alarming rate. It's a critical topic given that the vast majority of the extra heat trapped by greenhouse gases, over 90%, actually goes into the ocean.
That's right, Chloe. Ocean heat content has become one of the most reliable indicators of the entire climate system's health. Researchers, Trendberth and his team, analyzed global temperature readings from the surface down to 2,000 meters, covering the period from 2000 to 2023. They used a high-quality data set, IAP v4, which compiles information from thousands of Argo profiling floats and other instruments, allowing them to track energy accumulation across different latitude bands.
So, what did their extensive data reveal about where this heat is concentrating?
When they averaged the data across entire circles of latitude, a very clear pattern emerged. While the deep tropics are warming, that signal tends to fluctuate year to year because of how El Niño and La Niña events shift heat around the Pacific. However, the mid-latitudes show a steady and pronounced rise. Since 2005, the areas around 40 degrees north and between 40 and 45 degrees south have experienced the most substantial increases in ocean heat content.
That's a very specific finding. And you mentioned the southern belt is particularly intense. What makes that region stand out?
The southern belt is indeed the most intense. A large expanse of ocean between 35 and 50 degrees south has absorbed more heat than almost any other location on Earth. This area includes the famously stormy Southern Ocean and the waters flowing towards the South Pole.
It's easy to assume that increased solar energy reaching the top of the atmosphere would drive these warming patterns, but your findings suggest something more complex is at play here, don't they?
Exactly. The study shows this isn't simply a case of more sunlight leading to more heat below. While radiation at the top of the atmosphere has increased in many places due to rising greenhouse gases and declining reflective aerosols, these sharp ocean bands at 40 degrees north and south don't directly align with that pattern. Instead, they correlate with changes in how the ocean and atmosphere redistribute heat.
So it's more about movement than direct input. Can you elaborate on the mechanisms driving this redistribution?
The team integrated satellite radiation records with detailed reanalysis of winds, humidity, and temperature. They found that surface heat fluxes, storm tracks, and large-scale currents essentially operate like a series of moving conveyor belts. As the mid-latitude jet streams and storm paths shift towards the poles, the westerly winds above them also change. This alters the wind stress on the ocean's surface and impacts what's called Ekman transport, which moves surface waters sideways and causes either upwelling or downwelling.
That's a fascinating connection between atmospheric circulation and ocean warming. Can you give us specific examples of how this plays out in the two warming belts?
The southern hemisphere, stronger, more poleward westerlies are effectively pushing warm water into that band around 40 degrees south, while cooler deep water surfaces elsewhere. In the northern hemisphere, currents like the Gulf Stream and Kuroshio are transporting heat into the waters east of North America and Japan, intensifying the warming in the belt near 40 degrees north. One of the authors described this new pattern as, quote, very striking, end quote, noting how rare it is to see such a clean signal emerge from often noisy climate data.
It's a powerful signal, as you say. But on top of this human-caused warming, there must also be natural climate variability at play, correct?
Absolutely. While the long-term energy buildup is driven by human-emitted greenhouse gases, natural variation is clearly involved. El Niño and La Niña continue to redistribute heat in the deep tropics, which explains why the warming there appears patchy rather than steady. Additionally, long-term climate patterns, like the Pacific Decadal Oscillation, have been in unusual phases recently, potentially contributing to higher than normal sea surface temperatures outside the tropics. There's also the factor of aerosols.
How do aerosols fit into this complex picture?
There are fewer reflective particles in the air now due to cleaner ship fuels and reduced factory pollution in some parts of the northern hemisphere. This means a little more solar energy reaches the ocean's surface. Scientists think this might have exacerbated recent warming in the North Atlantic and North Pacific. However, this new study concludes that aerosols cannot fully explain the specific size and shape of these ocean heat bands.
So even with these insights, are our climate models able to fully capture the extent of this record-breaking heat?
Climate models can explain many of these processes, but they haven't been able to fully replicate the complete extent of the record-breaking heat seen since 2020. The authors suggest this gap is still under investigation, possibly stemming from both model limitations and the unfortunate coincidence of natural changes stacking on top of the steady human-induced forcing.
This detailed understanding of where the ocean is warming fastest might seem a niche scientific point, but what are the real-world implications for those of us living near these warming belts?
The implications are significant for everyday life. Warmer mid-latitude oceans intensify marine heat waves, which severely damage coral reefs, kelp forests, and fisheries. Extra warm water also evaporates more easily, adding moisture to the atmosphere. This can lead to stronger storms and more intense downpours when weather systems pass overhead, contributing to flooded streets, swollen rivers, and longer power outages. Furthermore, warm water expands, so heating the ocean in these specific areas means coasts within these bands are likely to experience sea level rise faster than the global average, compounded by ice melt in Greenland and Antarctica.
The message truly is clear then. The Earth continues to heat up. The oceans absorb the majority of that energy, and now winds and currents are channeling much of that extra energy into these two strong mid-latitude belts that circle the globe. If you found this conversation insightful, please share this episode with someone who would appreciate learning more about ocean warming.